a binomial, that means we have two terms that's being squared. Again, we do not want to use an exponent property here because exponent properties only applies to a base that is multiplication, a bunch of factors, or the base is a division problem. So here we use what it means to square something. We have 8x minus 3 times 8x minus 3. And then we go to work like we did in number 1 earlier. We use our distributive property twice. We get 64x squared minus 24x. Notice, because these two factors are identical, when we now take the second term times 8x, we get an identical term to the second term right here. These are always going to be identical, and negative 3 times negative 3 is 9. So when we simplify, we add these two terms, we get minus 48x plus 9. Here's our answer. So this type of problem is one that we often will ask true-false question of, and often we might do something like this, 8x minus 3 squared, and we'll say equals 64x squared plus 9. And that's false, and that's to help you discern that we do not apply the exponent properties here because it is a subtraction problem as the base. Factor completely. I often fool around with my my algebra students and say that when it comes to factoring, you should have GCF tattooed on your hand somewhere, because this is the first form of factoring, and it's often the one that people forget about. But without factoring out the greatest common factor, you could have a lot of difficulty, or it's impossible to factor this. So GCF here is 2 factors of x, or x squared, is common in each one of these terms. So when you factor out the x squared, what you're left with is x squared plus x minus 6. So this is now factored, but it's not completely factored because we now can write this second factor, x squared plus 1x minus 6, as 2 more factors, x plus 3 and x minus 2. So this is now this expression completely factored. The next question asks you to find the cube root of negative 125. A common mistake here is some students forget that cube roots, you can take the cube root or any odd root of a negative number. You confuse it with even roots. Like you can't take the square root of negative 125 and get a real number. So in this particular case, you're asking what number can I cube, which means what number can I multiply 3 times and get 125, and that negative 125, and the answer is negative 5. Number 9 is another factoring problem. This is a situation where you notice that 16 is a perfect square. And since x to the 4th has an even exponent, it's also a perfect square. So we refer to this as the difference between 2 perfect squares. And these problems are very easy to factor once you recognize them. And you can usually only recognize problems like this once you've done lots of practice. So in this case, x to the 4th and 16, both perfect squares. There's a difference, a subtraction in between them. We refer to it again as the difference of 2 perfect squares. So you say, what do I square to get x to the 4th? X squared. What do I square to get 16? 4. Now, notice we don't have a middle term here. There's no middle term. And that's because we had a plus and a minus in the factors. And notice 4x squared, take away 4x squared gives us that 0x squared. Now, you might be happy with yourself and think you're all done, but notice this second factor here is again the difference between 2 perfect squares. So we need to keep going. The first factor cannot be factored any further, but the second factor becomes x plus 2, x minus 2. Okay, so I'm going to if my colors will work for me here, I'm going to have x squared plus 4. I'm going to keep that the same color. And now this one becomes the two factors, x plus 2, x minus 2. So sometimes you have to, you can only factor something once, like sometimes you can only pull out a greatest common factor and you're done, but you should always look at the factors that remain to see if you can continue to factor them. So this is what we call factored into its prime factors. Both of these problems here factored all the way down into prime factors, which means you cannot factor either one of these three factors, any one of them, any further. Okay, we're dividing by fractions here, and regardless of whether we have numbers or algebraic fractions, we know that when we divide by anything, it's the same as changing division to multiplication by the reciprocal of your second fraction in this case, or your denominator. Okay. Now, before I even try any attempt here to simplify this, I need to factor everything. So I'm going to write one big long fraction bar, and I see on top I have 6 times x squared times x minus 1. I can't simplify either of those three, any of those three factors. However, the bottom denominator here, again, recognizing it's the difference of two perfect squares, so that's x plus 1, x minus 1. So I'm going to write that down here, x plus 1, x minus 1. And then this denominator, again, don't forget, GCF, your friend, it's your greatest friend in algebra. If you factor out an x, you get 3x plus 1. So now we have x times 3x plus 1. So we have 4 factors in the denominator now, instead of the original 2, because we factored each one. And now we look for a common factor that exists in both the bottom in the denominator and the numerator, because that common factor is like a 1. It is a 1. You're dividing something by 1, which doesn't change it. So you notice you have an x minus 1 and an x minus 1. That's the factor of 1 that you're dividing out when you reduce something. And then don't forget, you have x to the first power with x squared leaves you with just 1x. So you get 6x in the numerator and x plus 1 times 3x plus 1 in the denominator. So this is completely simplified. There's no need now to multiply these two binomials back to be in 3x squared plus 4x plus 1. You could if you wanted to, but you might as well keep it factored so that you avoid the temptation of canceling parts or terms of the fraction. Okay, to add, we need to have like fractions, like anything when we add. Both of these denominators are prime, so to create the common denominator, the least common denominator, you simply multiply the two prime expressions, the two prime factors here. This is now your common denominator. So you need to change each fraction so that it has this common denominator. So this first fraction, if you want to create this common denominator, I'm going to make the first denominator blue, and I'm going to make my second denominator red. So lots of times it's just simply saying what's missing when you compare these two. When you look at this first fraction and you compare it to the second fraction. When you compare it, you see that the second fraction has x minus 3 in the denominator. So you need to multiply the top and bottom of your first fraction by x minus 3. Let me remove this for now. So this first fraction, x over x plus 3, is the same as x times x minus 3 over x plus 3 times x minus 3. Because see, all I did was multiply this by 1. So I didn't change it. I raised it to what we call higher terms. So I'm going to rewrite that again. X times x minus 3 over x plus 3 times x minus 3. Now I'm going to add. Now this second fraction, remember, it now looks like this, 5 over x minus 3. And I want it to look like x plus 3 in the denominator times x minus 3. So when I compare the two, I say, well, this fraction already has x plus 3 as a factor in the denominator. To make it look like this new fraction, I'd have to write x minus 3 in the denominator, but I'm not allowed to change this fraction by multiplying just the denominator by x minus 3. I have to multiply both the top and bottom. So that now gives us 5 times x minus 3 over x plus 3, x minus 3. So those are our two new fractions that we now can add because they have common denominators. So at this point, I just put one big long fraction bar. I put my least common denominator with my two factors in the bottom. And now I look at multiplying each of the tops. X times x is x squared. X times negative 3 is minus 3x. So I've taken care of the multiplication of my first numerator and add 5x and negative 15 or take away 15. So hopefully I'll be done with this soon. Let's see, x squared, I get to add these two because they're like to 2x minus 15. And then I have x plus 3, x minus 3 on the bottom. And you might think you're all done, but remember, you always have to ask, can I reduce this fraction? And the only way you can ever reduce any fraction in arithmetic or algebra is to ask if it has common factors. Well, the problem is the top is not factored. So the only way you can answer that is to factor the top. So to factor the top, I look at two binomials. X times x gives me x squared. And I'm looking for factors of 15 that differ, because of that subtraction sign, by 2. Well, factors of 15 that differ by 2 are 5 and 3. And since I ended up with a plus 2x, I'm going to have the plus in front of my 5 and the minus in front of my 3. And now I put my denominator in, my lowest common denominator, and there's my reduction right there. There's my common factor of 1. So we have x plus 5 over x plus 3. Now here's a little tip. Notice I kept these in parentheses so you can clearly see that x plus 5 divided by x plus 3. They're not the same factor, because what happens is when you drop those parentheses, you have a very evil temptation creeps up into your hand and you want to cancel those x's. Those are not common factors, they're terms. That x plus 3, if we were to ask what two fractions gave us this fraction, it would be these two fractions you would have had to add with the common denominator of x plus 3. So you can't just take away the x here, because the x plus 3 is the common denominator for both the x and the 5. So that may be more than you want to hear, but that's one of the typical errors that a lot of students make. So that's why I keep the parentheses around my factors. Number 12, we're moving on to those pesky rational number exponents, or excuse me, the fractional exponents would probably be easier for you to recognize. And when I see problems like this, I think of them several different ways, but I think I'll take the easiest route with you. There's three things going on here. You've got to deal with the negative sign, you've got to deal with the 5, and you've got to deal with the 2. So I'm going to number these three things. You've got three sort of operations you have to perform here. You've got to deal with whatever it means to have a 2 in the denominator of your exponent, the 5 in your numerator, and then that particular negative sign right there. So let's take, I'm going to erase some of the earlier work so it gives us some room here to work. So let's see, we have 16 to the negative 5 halves. So I always encourage students to do this first, which says take the square root. Your roots are in the denominator. And if you grew up in a farming community, you know your roots are in the cellar. On a farm, you put your potatoes, your beets, your carrots in the cellar. The roots always go in the cellar. So the first thing I do is take the square root of 16 and I get 4. This is the positive square root of 16. I get 4. And then what's left is this minus 5, negative 5 for my exponent, because I've taken care of that square root by writing this as 4 to the negative 5. And now the next thing I would do is I would now apply raising this to the 5th power. So 4 times 4 times 4 times 4. Oh boy, 16 times 16. Oh, I've got to do this one out. 256. So this becomes 256 to the negative what? Negative 1. That's what's left is a negative 1 because you've applied the 5th power to the base of 4. Now all that says is put that 256 in the denominator instead of the numerator as 1 over 256. So that's one way to do this problem. As you can see, you wouldn't want to, I should write here second step so you don't confuse that with another exponent there. You don't want to take 16 and raise it to the 5th power. That would be a huge number, and then you'd have to figure out what the square root of that number is. Also, unless your base is a fraction to start off with, I always save the inversion to the end. Now I'm just going to pull up another page here, and I want to show you something that I see happen a lot with students around fractional exponents. Students sometimes know when they see that negative exponent that somewhere along the way they have to create a fraction or invert. And so what you do, some students do that's not correct is they actually invert the exponent itself. Now you've completely changed this problem. Now you're asking for the 5th root of 16 squared and then change the position. So you can never change the exponent itself by inverting it. That will not create an equivalent problem. The last thing I'd like to show you is that you could write 16 as 4 squared, for example. Why did I pick 4 squared? Because the denominator is 2, and here your exponent is 2. So when I apply my exponent properties, 2 times negative 5 halves, I multiply when I have a power to a power. My 2's cancel, and I'm right back to where I was a few steps ago, 4 to the negative 5, which is negative 1 over 256. Let's come back to the class activities. We've got 3, oh no, we've got 4 more to do. Okay, so now we rightly get to use our exponent properties here because everything you see inside those parentheses is multiplication. So you're set to go by applying the power of 4 to both of these factors. 2 to the 4th times x to the 5/4 raised to the 4th power. Often students forget about the 2 or whatever the constant is in front of your variable expression here. So this is 16 x to the 5/4 raised to the 4th power. When you have a power to a power, you're going to multiply. So that's 16 times x to the 5/4 times 4 over 1. The 4's will cancel or reduce, and you get 16 x to the 5th. 14 involves a multiplication problem, and they've decided to group the first 2 factors times the second 2 factors. There's no rule saying you have to group it that way. So you can drop these parentheses and write out each one of these factors as 4 separate factors. And then with the commutative property, you could put your two constant numbers, 5 times 4, together beside each other, and then your x to the 1/2 times x to the 3/4 beside each other. So 5 times 4 is 20. We're multiplying with like bases, so we keep the base the same and we add the two exponents. 1/2 and 3/4 is the same as 2/4 and 3/4, which is 5/4. So our answer is 20x to the 5/4. 15 is similar to one of our earlier problems, except for it was under a radical sign. I think it was in the class activities, or maybe it was earlier in our preview activities. No, right here. It's very similar to this, except it's under one. It's not under a radical, but the properties of exponents still apply. So this is 72 over 9 times x to the 6 over x squared. So 72 divided by 9 is 8. X to the 6 divided by x squared. Again, if you forget, you could do it out the long way. Reduce by finding your common factors of 1, and you see you have x to the 4th left, so 8x to the 4th. We're almost done. Reduce. Well, this is kind of a funny fraction, isn't it? Some of you who may recognize it, this is the type of fraction you get when you are trying to solve a quadratic equation and you get x, or whatever your variable is, equals, and you get an expression similar to this. What's very important here is that you recognize that the denominator, I'm going to separate this out into the two expressions that's represented here. Let me get my eraser and put a 5. These are the two values that are put into this single fraction here with that little plus and minus sign. And what's really critical for you to understand is that the 5 in the denominator is part of both terms in the numerator. In other words, it's what I showed you earlier. If you asked, what two fractions did I add to get this fraction? It would be 10 over 5 plus 5 square roots of 2 over 5. Because in order to add, you have to have the same denominator. They have to be like. So often I encourage my students to separate out the two fractions and then simplify each one. So this becomes 2, and this becomes the square root of 2. So similarly over here, you have 10 divided by 5 minus 5 square roots of 2 over 5. So you get 2 take away the square root of 2. So if you wanted to express that with the plus and minus sign, this is what it would look like. Another way to do this problem is to actually factor the top by pulling out your common factor of 5. And what's left would be 2 plus or minus the square root of 2. And then your denominator is 5. And now because you have multiplication, you could cancel out the 5, and you still get the same answer, 2 plus the square root of 2 and 2 minus the square root of 2. What you don't want to do is cancel this 5 with just reduce this by canceling the 5 with just one of the terms on the top, because the 5 belongs to both of them. Okay? Belongs to both of them. So that's two approaches to number 16. 17 is a problem that often gives students nightmares, because not only do you have the 0 for an exponent, but then again you have the fractional exponent. So recall that if you have anything to the 0 power, the definition is 1, with the exception that x itself cannot be 0. So any number to the 0 power, except for the number 0, is defined to be 1. 0 to the 0 power doesn't exist. Okay, there's no number that 0 to the 0 power equals. So this becomes 1, and now you've got to deal with 32 to the negative 2/5. So let's review our earlier steps. We're going to do the root first, we're going to take this exponent second, and we're going to apply that positional change here with the negative exponent third. So the first thing I'm going to do is take the fifth root of 32, which is the number 2. 2 times 2 times 2 times 2 times 2 is 32. So this equals 2 to the negative 2, because I've taken care of the fifth root. 2 to the negative 2 is 1 over 2 squared, which is 1/4. So this becomes 1 take away 1/4, which is 3/4. Now finally, we have a reduction problem. We have a fraction, an algebraic fraction, and you want to remember that the only way we can ever reduce anything is by finding a common factor to the numerator and denominator, which is the factor of 1. So right now, neither the numerator or denominator is in factored form. It's an addition and subtraction problem. You have 3 terms on the top and 3 terms on the bottom, and never should a slash go through terms, only factors. So you factor your top, you say, what factors of 10 differ by 3? 5 and 2. X plus 5, x minus 2. And I chose to put the plus with the 5 because I noticed that when I do my distributive property here and I add my middle and outer term here, I end up with positive 3x. And if you happen to put x plus 2 and x minus 5, you can check it really quickly with multiplication, and you would get negative 3x in the middle. So all you have to do is just switch spots. Now the bottom says factors of 8 that differ by 2. Again, I know the factors of 8 that differ by 2 are the numbers 4 and 2. And since my middle term is positive, my biggest factor gets the plus and my smaller factor gets the negative. And you're happy now because you see your common factor of 1. So this reduces to x plus 5 over x plus 4. And I keep my parentheses so I don't have a temptation of canceling terms. So I hope that helps you with the class activities. If not, or if you still have some questions, you could use your discussion board and ask a classmate on Moodle if you're in our online class, or if you're in the day class, you could, in the face-to-face class, you could send me a note.